Hi, my name is Kai David, and I'm here today to talk about multi-objective particle swarm optimization for physically informed neural network. So let's define what it is a physically informed neural network. It is a neural network specialized to solve partial differential equations. It takes advantage of the gradients that are computed during the forward phase of the network training to calculate the residual error. And then it will use this residual error and the data error to guide the training of the neural network. We also have to discuss what is particle swarm optimization for PINNs. It is a method to train the PINNs using particle swarm optimization. We encode all the neural network into a vector. So each weight and bias here will be a position on this vector theta. And then we create a number of neural networks, each one represented here by a theta. And this vector would be our swarm. The goal here is to train a PINN as a multi-objective problem. So instead of use this scalarization function, we are training in all those dimensions. Each loss will be a new dimension for this multi-objective problem. The method used here is pretty similar to what we have on PSO PINN. We just make some changes to make it multi-objective. First, we have to start initialize the archive to hold the Pareto front. And then we update all the positions and check if the position is not dominated by the archive. If not, we append the new position to the archive. And after a number of iterations, we return the archive, which is actually the Pareto front. We use the diffusion equation as an example here. And we define the loss objective vector as this vector of two positions. There's a couple of reasons to use composed losses here. The first is to visualize better the Pareto front. It will be easier to see if we use just two dimensions. But most importantly, some of those losses should not be placed alone. The residual loss, for example, may yield infinite solutions if it doesn't have the origin position loss to anchor somehow the solution. And there are the results. Notice that we use not only the PDE information, but also we add some data. We created 10 points equally distributed over space and time. And in order to make it better illustrative, we add some bias noise to those points. Each line on this left graph represents one of the solutions on the Pareto front. The yellow dot here on the top is the best result for the residual loss. The red point here on the right bottom, it is the best result for the data loss. And this green point here is the minimal Euclidean distance to the origin of the Pareto front. Notice that it makes no point to discuss which is the best solution here, because all the solutions in the Pareto front are by definition equivalent. And this paper introduces novel training strategies for physically informed neural networks. It set and evaluates the influence of the analytical model and trained data. And also, this is a work that it is still in progress. We aim to give some elasticity for the PINNs. And that's it. Thank you all.